This is the answers for the Chapter 7 test that you guys took, and we'll start with a multiple choice section. Okay, so in number 1, in a study of the effects of acid rain, a random sample of 100 trees from a particular forest is examined. 40% of the trees show some sign of damage. Which of the following statements is correct? So when it says 40% of the trees from the random sample of 100 trees, that tells me that 40% is a statistic. It can't be a parameter because we don't know it's true for the whole population. 40% of all trees in the forest show some signs of damage. We don't know that. We only know that 40% of our sample show those signs of damage. And we certainly wouldn't know if it's more or less trees than that in the forest. So question 2, the sampling distribution of a statistic is the probability that we obtain the statistic in repeated random samples. No, there does need to be random sampling, and there does need to be repeated random sampling for a sampling distribution, but it's not the chance that we get a certain value of a statistic. So let's look at B. The mechanism that determines whether randomization was effective. Well, that doesn't have anything to do with repeated sampling, so it can't be B. C. The distribution of values taken by a statistic in all possible samples of the same sample size from the same population. And that's exactly what it is. So it's all of the values that are taken by a statistic, so think X bar or P hat or whatever, if we did repeated sampling, which is where it says all possible samples. And if we look at D and E, the extent to which the sample results differ systematically from the truth, that's talking about bias. And E, the distribution of values in a sample of size n from the population. So E is talking only about a single sample, not a sampling distribution. So it cannot be E. Number 3, a statistic is said to be unbiased if the correct answer is B, the mean of its sampling distribution is equal to the true value of the parameter that is being estimated. That's what unbiased means. So if we had a population here, even if the population was skewed like this, and let's say its true mean was here at, I'm just going to make up a number like 50. Then if we looked at the sampling distribution for that population, let's say we looking at samples of some really big size, like 1,000, so we're pretty sure that the sampling distribution is going to be normal at this point, then the mean of this sampling distribution must also equal 50. That's what an unbiased estimator or an unbiased sampling distribution means. The mean of the sampling distribution is equal to the mean of the population, or the parameter that we're trying to find. Okay, number 4. Which of the following distributions has a mean that varies or changes from sample to sample? The population distribution, well, that has only one mean. If I sampled the whole population, it's going to give me the exact same mean every single time since it's the whole population. So it's not one. The distribution of sample data, well, every time I take a different sample, I will probably get a different mean, or it will have a different average. And then the sampling distribution. Well, again, if I'm creating the sampling distribution from all samples, each sampling distribution is going to be the same because they're comprised of all of the different samples that are possible. So the sampling distribution looks the same. So the correct answer is B, number 2 only. All right, let's move on to number 5. Okay, so if you take a simple random sample of 25 things from a very large population in which the true proportion P equals 0.1, and this violates the condition that you have 10 successes and 10 failures, which statement below best describes what you know about the sampling distribution of P hat? So if you go back to your conditions for creating a sampling distribution for p hat, we see here that we don't really know how big the population is, but we know that the sample size is 25, and it tells me that it's a very large population. So I'm pretty sure that my sample size is less than 10% of the population, just because it tells me it's very, very large. Because that is true, I am allowed to use my formula for standard deviation of p hat, which is p times 1 minus p divided by n square rooted. It has nothing to do with being normal or not, but anytime my sample size is less than 10% of the population, then I'm assuming that my probabilities aren't going to change very much every time I take an object out of the population. So this is the formula we are allowed to approximate standard deviation. Okay? Now, the other part of this is, well, what is the shape of the sampling distribution going to look like? Because I don't have 10 successes and 10 failures, I have not met the large counts condition. And because I haven't met the large counts condition, I cannot say that the sampling distribution is approximately normal. So B says it's approximately normal, C says it's approximately normal, and then A, D, and E say it's not approximately normal. And in fact, if you think about it, because the proportion is 0.1, if I looked at the sampling distribution of this, 0.1 is here, 0.2 is here, 0.3 is here, 0.4 is here. It's probably going to be skewed closer to 0.1 because the sample size isn't very big, and then go down here, right? Because you just don't have this other side in order to get the symmetry that you're looking for, because you run into 0. So because my population is less than, or my sample is less than 10% of the population, I can use this rule to find the standard deviation. So I can use this formula here, and the distribution is not going to be approximately normal. Number 6, the number of hours in a light bulb that a light bulb burns before failing varies from bulb to bulb. The distribution of burnout times is strongly skewed to the right. But the central limit theorem says what? Well, the central limit theorem says as my sample size increases, it doesn't matter if my population is skewed to the right, to the left, or anything else. As my sample size increases, then the sampling distribution is going to become closer and closer to normal. So the correct answer is E. The mean burnout time for a large number of bulbs is close to normal. So if we looked at all of those different means that you could have, as my sample size increases, that's going to get closer and closer to normal. All right, number 7. You take a simple random sample of size 500 from the 37,000 students at Purdue University and measure their heights. You then take an SRS of size 500 from the 4.4 million adults in the state of Indiana and measure their heights. Assuming the standard deviation of individual heights in the two populations is the same, the standard deviation of the sampling distributions for Indiana is what compared to the sampling distribution for Purdue? Now remember, both of these have a sample size of 500. When we are calculating the standard deviation of a sampling distribution, we take the population standard deviation and divide by the square root of n. It says we assume that the standard deviation of individual heights in the two populations is the same. So we would use the same sigma for each of those. Here I would divide by the square root of 500. Here I would divide by the square root of 500, which tells me that the standard deviations are about the same for each sampling distribution. So the correct answer for number 7 is A. They're approximately the same because both have samples of size 500. Number 8, the chipmunk population in a certain area is known to have a mean weight of 84 grams and a standard deviation of 18 grams. A wildlife biologist weighs 9 chipmunks that have been caught in live traps before releasing them. Which of the following best describes what we know about the sampling distribution of means for the biologist's sample? All right, so we know that they have a mean weight of 84 grams and a standard deviation of 18 grams. That's true for the population. So for my whole population, the mean is 18. For the whole population, the standard deviation, oh, sorry, not 18, 84, and the standard deviation is 18. We're taking a sample of size 9, so the mean of my sampling distribution should be the same as that of the population, and the standard deviation of the sampling distribution is going to be the standard deviation of the population divided by the square root of the sample size, which in this case is 9, but the square root of 9 is 3, and 18 divided by 3 is 6. So we can eliminate A, D, and E. The mean is 84, the standard deviation is 6. However, what do we know about the shape of the distribution? If we go back to the problem and read it, the chipmunk population has this mean weight, has this standard deviation, blah, 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 blah. We don't know anything about the shape of the distribution for the entire population. My sample size is pretty darn small, so I can't assume that the sampling distribution is going to be approximately normal. I don't really know what its shape is going to look like because I don't know what the shape of the population is. So the correct answer for number 8 is B. In number 9, interpupillary distance, IPD, is the distance between the center of the pupils of a person's left and right eyes. So, you know, here's your eyeballs, and we're just measuring that distance. That's your IPD. In adult males, it's approximately normally distributed with a mean of 62.5 and a standard deviation of 6. If you take a simple random sample of 5 adult males, what's the probability that their IPD is greater than 60? So if you look at our sampling distribution, we're looking for a distribution whose mean is the same as the population mean. So that would be 62.5. But the standard deviation of this would be 6 divided by the square root of your sample size, which is 5. So now what we're saying is, well, what's the probability that if I took that random sample, we'd get an IPD greater than 60 millimeters? So in my picture, that's here, and I would be shading this area. My z-score would be 60 minus 62.5, so my observation minus the mean, divided by the standard deviation, or 6 over root 5. And what we want is the probability that z is greater than that, because we want an IPD greater than 60. So we can eliminate this z that was less than, and it looks like the correct one is going to be here. My observation minus my mean divided by my standard deviation. So the correct answer there is C. And then my last multiple choice question. A survey asks a simple random sample of 500 adults in Ohio if they support an increase in the state sales tax from 5 to 6% with the additional revenue going to education. Let P denote the proportion. I think that's supposed to be P hat. Let P hat denote the proportion in the sample who say they support the increase. Suppose that in fact 53% of all adults in Ohio support the increase. So right there I know the true proportion is 53%. What's the probability that less than half the sample will support the increase? So my sample is P hat, and it's looking at 0.50 because half is 0.50. So if we were looking at a picture, the truth here is that my population is going to have a true proportion of 0.53. The standard deviation of my sampling distribution would be 0.53 times 1 minus 0.53, which is 0.47, divided by the sample size, 500, and then we want to take the square root of all that. So we can see that this, and this do not have the correct standard deviation. Correct standard deviations are here and here. So then what I'm looking at is my observation. My p-hat is 0.5. Looks to me like 0.5 is below 0.53, so that would be maybe about here on my picture. And I want to know the probability that less than half the sampling distribution will support. So I'm going to shade this area. So I'm going to do 0.5 minus 0.53 divided by the standard deviation, but the correct answer is going to ask for the probability that z is less than that value, because I want to know the probability that less than half the sample gives me that. Okay, so that's it for the multiple choice part, and we'll do the free response part in just a little bit.